We've spent a fair amount of time now talking about the nanoscopic world and the subatomic particles that are the building blocks of everything in the universe. Now imagine that you're a physicist, and while there's still lots left to sort out, you feel pretty confident that the standard model of physics, with its quirky quarks and boozy bosons, is an accurate description of the subatomic space. But there are still a few things that the standard model fails to explain, like gravity, for example. And then you begin to wonder, is the very premise that the smallest things are point-like particles, so small that they virtually have no volume or shape, like a tiny point, incorrect? If so, what could possibly be the shape of the smallest things in the universe? Well, what if particles were in fact made up of tiny vibrating strings? You could have open strings or closed strings that form a loop, and the different ways in which they vibrate could imbue all the particles we know of with different properties. Sound outlandish? Welcome to string theory. Outlandish as it might be, this and other alternatives to the standard model of physics provide us with provocative implications and certainly stimulate creative thinking, which is at the heart of scientific discovery. Even if ultimately each of these theories is shown to be inaccurate, as undoubtedly they will be, after all, science moves forward by rewriting itself, understanding why these theories have gained ground in the past few decades will tell us that much more about the world that we inhabit. Up until now, you're probably thinking that string theory is just another addition to the standard model. Instead of quarks and bosons being the building blocks of matter, these subatomic particles are made up of strings. So what? Well, in fact, string theory is fundamentally different, because it provides a putative explanation for why the building blocks of subatomic particles might be shaped like strings. The standard model does no such thing. It just predicts that these particles must exist, and because we've observed them, it treats the subject as resolved. But that's not very satisfying. Why do quarks come in 3 flavors, not 5 or 2? Why does an electron have 2 possible spin angles? How do we know there isn't another particle that we haven't discovered yet? And if we do, how would we incorporate it into the standard model? String theory is fundamentally different. It provides an explanatory foundation that is either right or wrong, but it's not infinitely modifiable. Let's explore why. First, why strings? Because strings have certain properties that make them good candidates for the basic units of all matter, unlike any other putative shape. We'll take violin strings as a starting point. A violin string is tied to the instrument at 2 points, but in between those 2 points, there's nearly an infinite number of resonances that the string is capable of creating, simply by changing its vibrational patterns. A violinist can play many different pitches and make many different sounds with only 1 string. So too can the strings in string theory. The different patterns of vibration of a fundamental string can lead to different forces and masses. So the different subatomic particles are simply manifestations of different vibrational patterns of strings. How might this work? Thinking again about the strings on a violin, if you pluck a string lightly, it vibrates just a little. If you pluck it with a lot of force or energy, it vibrates more vigorously. The amplitude of the sound wave that the vibrating string generates is larger. The difference between the peaks and the valleys is greater, and the wavelength is shorter. There is less distance between 2 peaks. The same is true of our subatomic strings. The shorter the wavelength and the larger the amplitude, the more energy the string has. Now, as Einstein taught us, there's a direct relationship between mass and energy. Greater energy equals greater mass. So the subatomic mass of a particle is determined by how vigorously a string is vibrating. The more frantic the vibration, the more mass the particle has. And here's where string theory seems to outdo the standard model. The more mass the string-generated particle has, the greater the gravitational force that it exerts. In fact, all of the fundamental forces, including gravity, can be translated in terms of the vibrational patterns of the strings. More satisfying than quarks and bosons and so on, right? In the Standard Model, each subatomic particle is different, made from different stuff. In string theory, they're all made of strings, just some vibrate one way and some another, giving them different properties. This is why string theory often includes musical analogies. It's the music of the spheres or the cosmic symphony. Different elementary particles are simply different notes played on the same strings. And so we begin to grasp why string theory is a candidate for the theory of everything. But what are strings supposedly made of? Well, they're made of strings. They're not reducible to anything. A melody is made up of musical phrases strung together. Each phrase is made up of chords or other clumps of notes. Each note might have a pitch value and a time value, how high it is, how long it lasts, but you can't reduce it to more than that without losing the essence of what a note is. In the same way, you can't reduce strings to anything else. If they were composed of other things, they wouldn't be the fundamental building blocks of matter. The big question, though, is why haven't we seen any strings yet? Because the theory holds the length of a typical string is about 100 billion, 10 to the 20 times smaller than an atomic nucleus. According to physicist Brian Greene, we would need an accelerator to slam matter together with energies some million billion times more powerful than any previously constructed in order to reveal directly that a string is not a point particle. Do you buy it so far? Hold on, it gets even stranger. We all experience the world in 4 dimensions, 3 describing space and 1 describing time. Spatial dimensions are roughly translated into left, right, backward, forward, and up and down, while time moves in one direction, from the past to the future. So, for example, I can pinpoint an event in my life with respect to where and when it happened. An address giving me the left-right point, its cross street describing the backward-forward point, which floor I was on specifying the up and down point. Then I can also tell you what time of day, on which day, in which year the event occurred. This 4-dimensional representation of our world and our experiences is so ingrained, so it's very hard for us to imagine the universe described in any other way. But string theory doesn't quite work in 4 dimensions. How is this possible? Remember that gravity, when Einstein described it, seemed to be a mysterious force that somehow affected large bodies from very long distances, with only space separating them. Einstein's genius was in suggesting that the space itself was the material on which the force acts. That space and time can be thought of as a large flat sheet, and the bodies that are massive create depressions in that sheet that affect the movements of nearby smaller bodies, like the sun affecting the orbit of the Earth, and the Earth affecting the orbit of the Moon. And according to Einstein, the fabric of space-time is constant. It's a smooth continuum that only very big things like planets and stars can warp. Remember, too, that Einstein had a real problem with the fuzzy nature of quantum mechanics. Why? Because if space-time is the fabric of the universe and it's smooth and constant, how is it possible that the smallest things, those elementary particles that make up everything, are in fact always moving about and shifting in ways that we can't predict or observe? String theory tries to reconcile the 2 theories by suggesting that the properties of the strings that make up the universe can yield gravity and all the other forces. The different ways in which the strings vibrate correspond to the particles of the Standard Model, including the force carriers. For the first time, the 4 forces are unified by the properties of vibrating strings. But it also goes one step further, proposing an idea that for many of us is the breaking point between the plausible and the fantastical. What if, in the fabric of space-time, there were other tiny dimensions that we couldn't see? For example, what if you delved deeply into the nanoscopic world, strings could move in the typical 3 dimensions and the 4th, the time dimension, but also in other dimensions around little loops at the edges of where our familiar 4 dimensions intersect? String theory theorists often suggest that we picture these alternative dimensions like the circumference of a thin wire. If you look at the wire from far away, as the nanoscopic world looks to us, it only has 2 dimensions. It looks like a flat line. But if you zoom in, you can see that it's actually a tube, and things that interact with it, like an ant on a telephone wire, can move in the 2 dimensions, but can also crawl around the circumference or around the wire. String theory suggests that that's how tiny the new dimensions might be, so small that we can't observe them. And there isn't just one, like the circumference of the wire, there are 6 of them. So, for the computations and predictions of string theory to be correct, there have to be 9 space dimensions, the 3 that we can observe, and 6 that we can't, and 1 time dimension, for a total of 10. 10! These extra dimensions intertwine with each other to create an intricate shape. Now, just like a cello and a violin make different sounds because the instruments have different shapes, so too might the vibrations of strings depend on the intricate shapes of these tiny dimensions. So, all of this sounds interesting, but very speculative. How might we gather evidence that will point to the existence of these extra dimensions? Well, the truth is that we don't really know yet what the tools might be that would allow us to observe these extra dimensions directly. But we can use our particle accelerators, like the Large Hadron Collider in Geneva, for example, to find some indirect evidence. Let's say that we smash 2 particles together and we calculate the amount of energy they start with and the amount of energy left in our familiar 3 dimensions after they collide. If there's energy lost that we can't account for, we might be seeing energy disappear into one of our mysterious new dimensions. A few years after string theorists posited that 10 dimensions were needed to make the equations of the theory work out, another version of the theory suggested that in fact 11 dimensions were needed to account for some of the features of gravity. Then another version was proposed that also seemed to be correct, even though some of the equations were tweaked. And then another, and another, until there were 5 versions of string theory, all with different equations, and all of which seemed equally plausible or correct. Well, that's quite a problem for theoretical physics. If we can't distinguish between these 5 theories, then how are we supposed to sort out which one is ultimately right? It's an untenable situation. Thankfully, in 1994, string theorists came upon a potential solution. What if all of these theories were actually correct and simply described the world from different points of view? The 5 theories might be the same thing, from different perspectives. So they proposed a unifying theory that incorporated all 5, and they called it M theory, with the letter M possibly standing for membrane or matrix, mother or monster, or even mystery and magic. Theoretical physicists, they're a pretty creative bunch. But M theory is generally thought of as suggesting that the strings are slices of a 2-dimensional membrane that vibrates in an 11-dimensional space. Now, admittedly, I'm being intentionally vague about the details of M theory because it's still only partly developed. What's worse is that because of its fuzziness, it hasn't yet yielded truly testable predictions, one of the fundamental properties of scientific theories. So, at the moment, it's still more of an idea than a theory, even though many of its details have been outlined mathematically. Some leading physicists have gone so far as to claim that it will remain ultimately untestable, which is a problem. But for some people, even the thought of testing the theory brings on fears of world-ending black holes created by particle accelerators like the Large Hadron Collider. Are these fears warranted? Could our curiosity kill us? Should we leave these mysteries well enough alone? To make these decisions, we need to understand the nature of black holes and how they might relate to M-theory. Simply put, a black hole is created when a star of sufficient mass dies. Stars are huge spheres of plasma, one of the four states of matter, the others, of course, being solid, liquid, and gas. You might remember from our fluid mechanics lecture that plasma is an electrically neutral medium that is created by heating up gas. Stars are essentially fusion bombs, smashing hydrogen nuclei together to create helium in very high temperature and high pressure reactions. These reactions release a lot of energy that radiates from the core, where they take place, out into space. Because stars are massive, the force that gravity exerts on them is very strong. So the shape of the star is a combination of gravity pulling things inward and the fusion reactions sending things outward. Once the fuel in the core of the star is burned out, gravity begins to win, and eventually the star collapses on itself, creating a black hole. The black hole created by a dying star is the highly compressed core, whose mass is so large that gravity prevents anything from escaping it, including light. The core's gravity is so strong, in fact, that some physicists believe that it sinks through the fabric of space-time, leaving behind nothing but a hole. The entrance or mouth of the hole is called the event horizon. The pull of the black hole's gravity and its distortion of space-time is so strong that anything passing near the event horizon, including light, gets sucked into the hole, never to be seen again. So beyond the horizon, no events can be perceived. Now, some people worry that in all the particle collisions that physicists are causing as they test their theories in giant accelerators, they might accidentally generate a black hole. These people are concerned that our whole planet could then be sucked into the hole and destroyed. Is that possible? The short answer is, well, no. It's true that the Large Hadron Collider is designed to mimic the conditions of the Big Bang, and it very likely does produce black holes. But they're so small that they almost immediately collapse. They don't have the gravitational pull of a massive core of matter the way that a star does. They do, however, tell us something interesting about the relationship between black holes and M-theory. Traditionally, we think of black holes as the most massive things in the universe, and M-theory as a description of the very smallest things. So, what do these two ends of the size continuum have to do with one another? Well, for one thing, both black holes and elementary particles have similar features. That is, they are characterized by their mass, electric charge, and spin. How can a black hole have charge and spin? Well, we say it has a charge because it repels other black holes, though this charge is so weak that it's virtually ignored. And we say that it has spin because it's predicted to slowly rotate on its axis, dragging space-time with it. You can imagine this effect by thinking about how you might dry a nectarine after washing it. If you rotate it in a paper towel, the towel will rotate a bit too. Einstein called this phenomenon frame dragging. And two black holes, or two elementary particles that have the same mass, the same charge, and the same spin are identical. You can't distinguish one from the other. So some physicists have suggested that black holes are like gigantic elementary particles. You can think of black holes as a thread that pulls together the laws of classical physics, including Einstein's theories of relativity and quantum mechanics. Large black holes have properties that are similar to elementary particles, but they obey the laws of classical physics, while micro black holes, the kind that are formed in the dimensions that we can't see according to string theory, obey the laws of quantum mechanics. By understanding black holes, we learn about elementary particles, and by learning about elementary particles, we might begin to understand black holes. Black holes also have something in common with the Big Bang. At their core, there is an unexplained singularity that we don't understand. What happened just before the Big Bang? What happens at the core of a black hole? At the very center of a black hole is what physicists call a gravitational singularity. Now, note that this term has a different meaning from a technological singularity, which Ray Kurzweil and other futurists predict is coming soon for artificial intelligence. The technological singularity is the emergence of intelligence in technology that surpasses our own, and the consequences of which we can't predict. A gravitational singularity, in contrast, such as what lies at the center of a black hole, is a curve in space-time that reaches infinity. The common denominator is that we can't predict the consequences, but the causes are very different. Technology on one hand and gravity on the other. Einstein's theory of general relativity predicts a gravitational singularity just before the Big Bang, which keeps the Big Bang shrouded in mystery. By extending the curvature of space-time to infinity, a gravitational singularity remains unexplained. Crudely put, the equations begin to unravel and the math just doesn't make sense. String theory and M theory have the same problem. But an alternative theory proposed in the 1980s provides an attractive answer. What if the core of the Big Bang is not nothing, but a very tiny, hugely compressed universe? And that the Big Bang isn't really a bang at all, but more like a big bounce. The universe gets very, very, very small, and then something happens to cause it to expand once again. This idea is a corollary of yet another theory called loop quantum gravity. The theory of loop quantum gravity emerged as an alternative to string theory and as an explanation of gravity at the quantum level. Reformulating the equations of general relativity, an Indian physicist named Abhay Ashtekar tried to reconcile general relativity with the rest of classical physics. Using these new variables, a number of physicists, including the current figurehead of loop quantum gravity, an American named Lee Smolin, realized that the history of the universe could be thought of in terms of intersecting loops. The implication of these loops, according to the theory, is that before the Big Bang, there was no singularity. The universe didn't emerge from nothing. It emerged instead from a tiny, crunched-down universe that preceded it. Instead of a beginning of everything, there's an infinite loop of which we occupy a small part, and during which the universe expands and contracts and expands once again for eternity. Hence the name the Big Bounce. Spiritually, this idea is comforting because it suggests that we don't have to end, that we can in some small way live forever, since whatever we're really made of is just part of a never-ending, infinitely looping universe. Now, who's to say that even if this were true, which is a big if, that by rearranging our bits time and time again, we'd ever really be ourselves more than once in any meaningful way? But that's beside the point for now. Ultimately, we are just recycled stardust, and yet we all feel like unique individuals. But recently, a small group of physicists have tested this hypothesis by modeling what happens at the core of a black hole. They applied the math of loop quantum gravity to a simplified model of a black hole and found that everything that was pulled into the hole didn't compress into a singularity to be forever lost. Instead, everything was compressed into a very small thing and then spit back out into the universe. Or alternatively, through a portal, into another universe entirely. So loop quantum gravity opens the door to the idea that there are, or were, or will be other universes besides ours. A loopy idea indeed. But unlike in M theory, there is no need for extra dimensions. The 4 that we can observe work just fine. As a side note, I should mention that Lee Smolin, by many considered the most vocal proponent of loop quantum gravity, has been quoted as saying that there is only one universe, since the term universe means, by definition, all there is. But he's also the first to argue that science progresses fastest when there's controversy and disagreement amongst researchers. In his 2006 book, The Trouble with Physics, he rails against the near monopoly that string theory has had in theoretical physics in the last few decades and lobbies for a diversity in funding and approaches. To that end, perhaps he would concede that the idea of multiverses or multiple universes should still be explored, since it provides some possible solutions to the major questions in physics, and quite obviously lends diversity to the field, not to mention the rest of reality. So before we say goodbye to the wild world of quantum mechanics, we should dip our toes into one last alternative idea, and that's the many worlds interpretation. Loop quantum gravity came about when the key equations of general relativity were reformulated to account for gravity at the quantum level. But what if, instead of tweaking our conceptualization of gravity to bring quantum mechanics and classical physics closer together, we instead tweaked quantum mechanics? String theory is one example of such a tweak. The many worlds interpretation is another. Einstein's problem with Schrödinger's cat was that God doesn't play dice, that uncertainty is not a solution. And so the many worlds interpretation suggests an alternative. What if, during each instance of uncertainty, both consequences happened, but in different universes? The cat was alive in one and simultaneously dead in another. Everything that could possibly have happened in the past has in fact happened, but in a different universe. Our universe represents only one of the many possible timelines, and it flows in one direction, from the past out into the future. But alongside our universe, there exist any number of other worlds in which every possible alternative event has happened or will happen. The many worlds interpretation has a substantial following in theoretical physics, and its implications continue to occupy some of the greatest minds of our time. But it's also immensely appealing to writers and purveyors of fiction. One of the great assets of our brains is our ability to consider the consequences of different actions. The many worlds interpretation stretches this ability to its limits, as we can indulge in detailed and far-reaching fantasies of what might have happened had we made a different choice in life. Theoretical physics is arguably the most imaginative of all the sciences, and for many of us who gravitate towards science because we prefer our feet solidly rooted to the ground, its thought experiments, its mind-bending theories, and their implications can be unsettling. Still, it's worthwhile to delve into these ideas, even in a fairly shallow sense, because in the true spirit of science, they raise far more questions than they answer. Physicists watching and performing the experiments conducted at the Large Hadron Collider were initially looking for the elusive Higgs boson, the last particle to be observed in the standard model of physics. And they found it. But so far, they haven't found any other shocking anomaly that might provide evidence or even a hint that the standard model needs to be enhanced by ideas like those presented in string theory. It's nice when your predictions are supported by your data. You can go home, make a nice dinner, have a glass of wine, celebrate a job well done. But it's so much more exciting when your experiment shows you something completely unexpected, and not simply because you didn't design it well or made some sloppy error. Instead, these new observations are at the very core of great scientific discoveries. And so far, much to the dismay of many physicists, the Large Hadron Collider hasn't produced any shocking, paradigm-shifting findings. So, with the discovery that the Higgs boson is much as the standard model predicted it would be, some of the excitement fueling string theory and some of these alternatives has been deflated. What if the Standard Model is really all there is, with a few tweaks to account for the missing links? In some ways, that seems more frightening because it means that what we observed is all there is. More frightening than the possibility of strings, extra dimensions, and many worlds. But there is still another way to think about the nature of the universe, the Big Bang, the formation of the galaxies, stars, black holes, and all of matter. The idea that the whole is in fact greater than the sum of its parts. This notion is at the very core of a relatively new field in science dedicated to studying complex systems. It's called emergence. It's a framework for understanding how we can get order out of chaos. And it's where we'll turn to next.